Good afternoon, everyone. Today we're going to be talking about substitution reactions and elimination reactions. So it'll be a two-part lecture. I'll do substitution reactions first, and then I'll follow up with an elimination reaction lecture. And what we're going to do is determine how we can identify which type of reaction will take place, draw the reaction mechanisms, or write the reaction mechanisms, and also draw the energy diagram for these types of reactions. Well, let's get started today. We'll be talking about substitution reactions, going over a little bit about what we discussed on class before spring break. And so we're going to first start off with talking about a certain type of organic reaction involving haloalkanes or alkyl halides. This is the class of compounds we'll be discussing. And the general form is Rx, where R is a unique type of carbon group, X is a halogen. And in particular, we're going to be discussing nucleophilic substitution. So we're going to be substituting one nucleophile for another nucleophile. Usually a stronger nucleophile with a weaker nucleophile with a stronger nucleophile, generally. And these are referred to as SN2, SN1 reaction. The S referring to substitution, the N referring to nucleophile, the 2 and the 1 referring to the number of the type of molecular step involved in the rate determining step. So for SN2, there are 2 molecules. It's a bimolecular step. SN1 in the rate determining step is a unimolecular step. Now, what is a nucleophile? A nucleophile means it's nucleophile. It loves positive charge. So it's something that is attracted to positive charge. And so these can either be neutral or anionic, and generally the neutral ones are weaker than the anionic ones. For example, we have ammonia, which is a nucleophile, and cyanide. Now these nucleophiles are attracted to positive charge. So on an organic compound, the most common type of positive charge we have is called a carbocation, where the carbon has a positive charge. And this is referred to as an electrophile. So an electrophile is looking for electrons. It wants negative charge. So it's attracted to negative charge. And again, the most common one that we use is carbocation. So it becomes a positive charge on the carbon. And so there are 2 types of mechanisms for these nucleophilic substitution reactions. The first mechanism is a bimolecular one-step mechanism. And this is referred to as SN2. So these are one-step mechanisms. And we'll discuss in a little bit how do we know based on the alkyl halide whether it's going to be a SN2 or SN1 reaction. Just for explanation purposes, another type of reaction or nucleophilic reaction we can have is SN1, which is a unimolecular 2-step mechanism. There are 2 steps in a SN1 reaction. The first step is the rate determining step, which forms what's called the carbocation. The second step, the nucleophile attacks, and you get your substitution. Now, just to let you know, methyl alkyl halides do not undergo SN1 reactions. This is just here for illustration. So methyl And the reason this is, as we'll get into a little bit, is that with methyl halides, so a methyl group attached to a halogen, the carbocation is unstable. It won't form a carbocation, so therefore you won't get what's referred to as the intermediate. So methyl halides do not undergo SN1 mechanism, which is a two-step mechanism. So before we begin, again, nucleophile is attracted to positive charge itself, is electron rich. There are two types, neutral and anionic. Anionic generally are stronger. Electrophile is what the nucleophile is attracted to. Electrophile is looking for electrons, so it's positively charged. The most common type of electrophile that we use in organic chemistry is a carbocation, meaning there's a positive charge on the carbon. So here we have this methyl bromide. The acetate is the nucleophile. It undergoes a bimolecular concerted. We call this a concerted reaction. Concerted meaning that it all happens at the same time. It's a bimolecular step for the rate determining step. And it's referred to as an SN2 reaction. It's only a one-step mechanism. So we can actually draw the energy diagram for an SN2 reaction. It would look something like this. So it's a one-step mechanism, and the one step is the rate determining step. So that's what the energy diagram of an SN2 reaction would look like. Now, generally, substitution reactions are exothermic, and we'll get into that in just a little bit. Now, for a SN1 reaction, what does its energy diagram look like? So again, for SN1, the rate determining step is a unimolecular step. That's where the one comes from, but it's a two-step mechanism. So there are two steps in the mechanism for an SN1 reaction. So now if we draw the energy diagram for an SN1 reaction, we'll see the difference. So remember, SN1 has two-step mechanism. So that means there's going to be two humps. So we start here, and the first step is the rate determining step. So that's one of the largest activation units. Then we form an intermediate, and then we have the second step. So an SN1 reaction has two activation energies. Activation energy 1, activation energy 2. The first activation energy is the rate determining step. It's the one with the highest. So always in SN1 reactions, the first step is the rate determining step, which is the slowest step. So it's going to have the highest energy. And then the intermediate is formed here, and it reacts with the nucleophile to form the products. Just to give you an idea of the basic energy diagrams for an SN1, SN2 reaction. I'll give you a few seconds to kind of look this over before I clear it and move on to the next slide. Okay. So now different types of nucleophiles. Oops, excuse me. So we have neutral nucleophiles such as H2O, amides, all different types of amides, alcohols. Alcohols usually form ethers in substitution reaction if the substitution is in the middle, or in general it forms ethers. Carboxylic acids usually form esters. Then we have charged nucleophiles, so we have alkoxides, which are very strong basic nucleophile, hydroxides as well. So they're all of these types of species are searching for positive charge. They're very negative. They want to get positive charge to balance it. So for an SN1 reaction, again, SN1, S meaning substitution, the N meaning nucleophile, the 1 meaning it's a unimolecular step. The unimolecular step and the rate determining step. So the rate law only has one species in it. But again, SN1 reactions are two-step mechanisms. Always in the first step, you form the carbocation. So the leaving group leaves, forming the carbocation. And then in the second step, and again, the carbocation is the intermediate. In the second step, we have the nucleophilic substitution. So then the nucleophile attacks the carbocation, forming your product. Now, for sure, primary and methyl halides do not undergo SN1 reactions. And the reason is because these generally do not form stable carbocations. So primary, again, primary and methyl halides, primary alkyl halides and methyl halides generally do not undergo SN1. So your primary alkyl halides and methyl halides tend to undergo SN2. And again, this is because primary alkyl halides and methyl halides do not form stable carbocations. And even secondary alkyl halides may undergo SN1 or SN2. Typically, it prefers SN2, but it could, in theory, undergo SN1. Now, tertiary alkyl halides undergo SN1 reaction, do not undergo SN2 reactions. Again, tertiary alkyl halides undergo SN1 reactions. So if you have a tertiary alkyl halide, and again, a tertiary alkyl halide has 3 R groups attached to the carbon that's attached to the alkyl halide. So again, you have 3 carbon groups attached to the carbon that's attached to the halide. And again, tertiary alkyl halides only undergo SN1 reaction because a tertiary alkyl halide forms a very stable carbocation. So again, tertiary alkyl halides, the reason it only undergoes SN1 reactions is A, they form stable carbocations, and B, for SN2 reaction, it has to attack from the backside, and with tertiary alkyl halides, the backside is crowded, and so it can't go through backside attack. So therefore, tertiary alkyl halides undergo only SN1 reactions. Because again, A, they form stable carbocations, and B, they're bulky, so there's no backside attack, which is needed for an SN2 reaction. So as you add more carbon groups, it becomes more favorable for SN1 reactions, aka you're increasing the steric hindrance. As you increase steric hindrance around that carbon attached to the halogen, you form a more stable carbocation, which means it's going to undergo SN1 mechanism. Now the least substituted, so if we go backwards, if we go in this direction, so if we go in this direction, the least substituted prefers SN2 reactions. So the lesser steric hindrance you have, or the less substituted alkyl halide you have, the more likely it's going to undergo SN2 reactions. So things like methyl halides and primary alkyl halides, that's why they undergo only SN2 reactions, because less steric hindrance, therefore the nucleophile can attack from the backside. Now, what does an energy diagram look like for an SN1 reaction? Again, SN1 is a two-step mechanism where the first step is the rate determining step. So always the first step is going to be your highest energy. It's going to take the most energy to form your carbocation, which is the intermediate in an SN1 reaction. This is intermediate. So again, the carbocation is always the intermediate. Then the nucleophile, in this case acetate, attacks the carbocation, which is what we see here. So the nucleophile, which is the acetate ion, attacks the carbocation, and you form, in this case, your ester. So again, for an SN1 reaction, typically it's going to be your tertiary substituted alkyl halides. The first step is the rate determining step. It's the slowest step. So it takes the most energy to form your carbocation. Then the nucleophile, in this case, which is acetate, attacks the nucleophile, forming your product, which in this case would be an ester. So it's a two-step process, but since the rate determining step is in the first step, only the alkyl halide affects the rate of reaction. So again, only the alkyl, for an SN1 reaction, only the concentration of alkyl halide affects the rate of reaction, because it's a unimolecular step. That's why it's SN1. But it's a two-step mechanism, but the rate determining step is unimolecular. So again, SN1 is two-step mechanism. However, the rate determining step is unimolecular. So there's only one reactant in the rate determining step, and that's where you get your rate law from. So here rate would equal K times the alkyl halide. For SN1 reaction, two steps. The first step is the rate determining step. Intermediate is the carbocation. After you form the carbocation, the nucleophile attacks the carbocation, forming your product. And generally, SN reactions are exothermic. Now for SN2 reactions, now here we're at SN2 reactions. It's a one-step mechanism, which is what we call concerted. So a concerted reaction, again, All happens at the same time. And the way this one step occurs is through what we call a backside attack. So the leaving group leaves from the front. So for example, in this drawing here, D is the leaving group. Excuse me, I apologize. No, D is not the leaving group. Excuse me. The bromide is the leaving group, so the bromide leaves, and then the nucleophile attacks from the backside. And this is why primary and methyl alkyl halides only undergo SN2 mechanisms because A, they're not bulky, so they can handle the backside attack as well. Now, tertiary alkyl halides do not undergo SN2 reactions because they're too bulky. Tertiary alkyl halides do not undergo SN2 reactions. Only SN1 for tertiary alkyl halides. Now, for the reactivity of SN2 reactions, like we talked about on the previous slide, the least substituted alkyl halides increase the reactivity of SN2 reactions. So the less steric hindrance, the more favorable the SN2 reaction is. So a methyl halide would have increased more reactivity than a primary alkyl halide. Again, tertiary alkyl halides do not undergo SN2 reactions. So now if we look at a SN2 mechanism, so again, this is a concerted step, concerted reaction. So the bromide leaves, and then the nucleophile attacks the backside of the alkyl halide. The transition state, what's happening is this carbon-bromine bond is getting longer. The carbon nucleophile bond is getting shorter. There's a bond starting to form between the carbon and the nucleophile, whereas the bond between the carbon and the halide is starting to elongate. So that's what's occurring at the transition state. And again, the nucleophile attacks from the back side. So the bromide leaves from the front, nucleophile attacks from the back, and we get our substitution reaction. Now, since this is a one-step mechanism, both the nucleophile and alkyl halide affect the rate. So again, it's SN2 reactions. It's a one-step bimolecular mechanism. And so since it's a one-step bimolecular, both the nucleophile and the alkyl halide affect the rate. So now let's look at an example of a SN2 reaction. Again, it's what we refer to as a concerted. Again, concerted, we've talked about it 3 times. Concerted means it all happens at the same time. The rate determining step is bimolecular reaction. So notice over here to the right, for a SN2 reaction, there's only one activation energy. Remember, for SN1, there were 2 humps. For SN2, there's only 1 hump. And generally, for substitution reactions, they undergo exothermic reactions. So here we look at this secondary alkyl halide. So this is a secondary alkyl halide. We have a nucleophile, and so the nucleophile in this, in lithium hydroxide, is the hydroxide ion. So since this is a secondary alkyl halide, what occurs is the bromine leaves, excuse me, the bromide leaves, it's our leaving group. The hydroxide attacks from the backside, and we get our secondary alcohol. And all of this happens at the same time. Yeah. Hydroxide attacks from the backside, the bromide leaves, we form our alcohol. Now notice here we use THF, which is a polar aprotic solvent. Don't forget about that. We're going to discuss that a little bit later. Just remember here for SN2 we use THF, which is a polar aprotic solvent. So why are SN2 reactions exothermic? So again, at the transition state, the carbon-bromine bond is breaking and we're forming a carbon-oxygen bond. Now what you have to remember is that the dipole, well technically a carbon-bromine bond, or how should I say this, carbon halide bonds typically have very poor dipoles. No, we won't put that. And so for a carbon-oxygen bond, it has a stronger dipole than a carbon halide bond. So since we're forming a more stable bond, the reaction is exothermic. So again, the carbon halide bond is less polar and in some cases non-polar compared to the carbon oxygen bond, which is a more polar bond. So since it's more polar, it's more stable. So since you're forming a more stable bond, energy is released. So we're going from a carbon bromine sigma bond to a carbon oxygen sigma bond. Again, the carbon oxygen sigma bond has a greater dipole moment, so its dipole moment is bigger than the carbon bromine bond, which has a very small dipole moment. And so since you're forming a more stable bond, it causes the energy to be released. So products are less energy than the reactants. So let's look a little bit more in depth about a energy diagram for an SN2 reaction. Again, here we have a methyl halide. So methyl halide, we already understand that if it's a methyl halide, it can only undergo SN2 reaction. We have a nucleophile that is a carboxylate or an anion. Since we're taking a carboxylate, reacting it with a methyl halide, we're going to create an ester. And so what happens again, SN2 is a concerted reaction. So both reactants are involved in the rate determining step. So what happens is this bond, the C bromine bond gets longer, the carbon oxygen bond gets shorter. That's what's occurring at the transition state. Notice there's only one activation energy for an SN2 reaction. And then you form your products. In this case is the ester and the bromide ion. Then these are characteristics of an SN2 reaction. For an SN2 reaction, you have both reactants. We start off in the first step. We only have one transition state, aka and activation energy. And we form our products. So now if we're comparing a methyl halide, excuse me, a methyl halide with a primary alkyl halide. How does the reaction diagrams look different from that? And so in this example, we're using both the same nucleophile. So the only difference between the two is one is a methyl halide, one is a primary alkyl halide. And so what we notice is that for the methyl halide, the activation energy is lower than when we're comparing the same reaction. The only difference is we have a primary alkyl halide. Because it's easier for the nucleophile to attack the backside of a methyl halide versus the backside of a primary alkyl halide. So that's why the methyl halide SN2 reaction has a lower activation energy than the primary alkyl halide. So higher activation energy means it's a slower reaction. It takes more energy to form products. So now we have an example here, and I wanted to have them hidden, but okay, we'll do what we dealt with. So in this example, we have a tertiary alkyl halide, and we have a methylamide, methylamine. My apologies, methylamine. I know organic chemists are gonna roast me if I don't get these things right. Yeah, methylamine and a tertiary alkyl halide. And since this is tertiary, we know that this is going to undergo SN1 reaction. So again, since we know that we're dealing with a tertiary alkyl halide, it's going to undergo the SN1 mechanism. So that's how we know it's SN1, is because it's tertiary. So what's the first step? That's right. The first step is we form our carbocation. So the iodine leaves and we form our carbocation. So if we were drawing the energy diagram for this, which I'll do right here, so again, we start with our reactants. The first step is the rate determining step. Which is the highest energy step. And then we form our intermediate, which is the carbocation. So it's the trying to freehand it here, so I apologize for the artistic. So again, first step is the rate determining step. Is going to have the largest energy. Now after we form the carbocation, the second step is when the nucleophile, which is our methylamine, attacks the carbocation. So that's the second hump. And then we form our products. And since it's a substitution, it's an exothermic reaction. And so therefore, since the first step is the rate determining step, so again, step one is the rate determining step. This is a unimolecular step. Therefore, our rate, not K, gee whiz, this should be rate K So rate equals K times the concentration of our tertiary alkyl halide. Again, the way we know it was SN1 was because we were dealing with a tertiary alkyl halide. It can only undergo SN1 reaction. Now we have a primary alkyl halide. So this is our primary alkyl halide, and we have methyl amine. So since we're dealing with a primary alkyl halide, this is going to undergo SN2 mechanism. So this is going to be a concerted reaction, meaning it's going to all happen at the same time. So what happens? The iodine, which is our leaving group, it leaves the nucleophile, which is the methylamine. It attacks, and we form our amine. Again, this all happens in one step. So if we were to draw the energy diagram of this one, the reaction progress. Sorry, I can't draw a straight line. We have our rate determining step. Cool. So this is a one-step bimolecular mechanism. It's one step because we only have one activation energy. So therefore, our rate, and again, I messed this one up again, should be K times the concentration of each reactant. That's what equals rate. So rate is dependent on both reactants for an SN2 reaction. Hopefully you've seen the difference between an SN1 and an SN2 reaction. I'll give you a second to mull this over before I clear the screen. Now let's look at some more questions. We have this reaction here. We want to identify the nucleophile in the following reaction. So we have a methyl bromide plus sodium hydroxide in water gives us methanol and sodium bromide. So here, the nucleophile, the most obvious nucleophile is the hydroxide from sodium hydroxide. So this is the major nucleophile that we have. But also, since we're using water, water is a weak nucleophile, so water can also, could also undergo nucleophilic substitution. So again, the hydroxide is the major nucleophile. HO is a minor one. It could, doesn't mean it would, but it could undergo a substitution reaction. But again, the major nucleophile is from sodium hydroxide. The OH, the hydroxide, is a very strong nucleophile, and it's also, we'll learn a little bit, a strong base as well. H2O is a weak nucleophile. So since OH minus is a strong nucleophile, it's going to be the one that more likely attacks the methyl bromide. Whereas water is a weak nucleophile. And again, bromide in this case is what we refer to as the leaving group. So bromine is the leaving group. Hydroxide is the nucleophile. It's a strong nucleophile. Water is a weak nucleophile. So here we want to know which of the following reacts the fastest by SN2 mechanism. So we want to know the fastest by SN2 mechanism. Fastest means lowest activation energy. So again, the fastest by SN2 reaction is going to have fastest movement. Which one's going to have the lowest activation energy? And for SN2 reactions, the least substituted alkyl halide would have the lowest activation energy. So again, the least substituted alkyl halide would have the lowest activation energy. So we look over here, the least substituted, well, A is a methyl halide, so it would be the least substituted alkyl halide, which would have the lowest activation energy, which would be the fastest SN2 mechanism. Now D would not undergo at all SN2 because it's a tertiary alkyl halide. So no, D would not be a choice. C, if we had to rank these, it would be 1, 2. Which ones would be the fastest? So A would be the fastest, followed by 2. And B and E, you'll learn about distinguishing those when you get to organic chemistry. So they may or may not undergo SN2. Depending on how stable the carbocation is, it may undergo SN1. But for the scope of this class, we'll just stick with the simple. You can wait till you get to organic chem, go more complex. But the one with the fastest would be the methyl bromide because it's the least substituted alkyl halide. Now, for substitution reactions, the solvent conditions do play a role in the reaction. So if you use different solvents, it can increase the activation energy or decrease the activation energy. And so, for example, if we're doing a substitution reaction, if we use a polar solvent versus a non-polar solvent for a substitution reaction, the polar solvent is going to be lower in activation energy than the non-polar solvent, because generally your nucleophiles like polar solvents. For example, hydroxide would not dissolve in, say, hexane as much as it would. It probably wouldn't at all dissolve in hexane, for a matter of fact. But hexane is a non-polar solvent. If you try to put sodium hydroxide and, say, methyl bromide, or not methyl, T-butyl iodide in hexane, the hydroxide will not dissolve. It take a lot more energy for that reaction to occur. But if you put it in a polar solvent, for example, such as methanol, it would lower the activation energy compared to a non-polar solvent because the nucleophile is more readily soluble in the polar solvent. So generally, So generally, if you have a polar solvent for substitution reactions, it's going to help lower the activation energy. Now we get into types of polar solvents. So there are two types of polar solvents. There's protic polar solvents, and then there's aprotic. Aprotic do not hydrogen bond. Protic have hydrogen bonding. So some examples of protic solvents, of course, these are like methanol, your alcohols, and water are the most common ones. Aprotic solvents, things like acetone, THF, DMF, dimethylformamide, amide, DMSO, etc. So acetone, THF, DMF, and DMSO, they don't have hydrogen bonding. They're called aprotic polar salts. They're polar, but they're aprotic because they don't have hydrogen bonding. Whereas alcohols and waters have hydrogen bonding. Now for SN1 reactions, if we look over here, for SN1 reactions, we prefer a polar solvent, but it actually, the best preference, the best is protic polar solvents. And the reason is why we want protic polar solvents for SN1 reactions, because it stabilizes the carbocation, and it does this through ion dipole interactions. So if you have a protic solvent like water, remember water has hydrogen bonding, which is a dipole-dipole interaction, the carbocation, positive charge. So what happens is the carbocation forms an ion dipole interaction with the solvent. In this case, it could be water and alcohol. It helps stabilizes it, so then it can continue through the reaction. So for SN1 reactions, the best solvents are protic polar solvents. They help lower the activation energy of your reaction. So if you had to choose for SN1 reaction, you would like to choose a protic polar solvent because it helps lower the activation energy. Now for SN2 reactions, it prefers aprotic polar solvents. And so what happens here if you use and again, aprotic polar solvents are things like THF, acetone, DMF, etc. And the reason we like aprotic polar solvents is because in SN2 reactions, protic solvents interact with the nucleophile, making it harder for it to attack the alkyl halide. So again, for SN2 reactions, we prefer aprotic polar solvents. They help lower the activation energy the best. Now, if you use a protic solvent, this interferes somewhat with the nucleophile by forming an ion dipole interaction between the nucleophile and the protic solvent, which makes it a little bit harder for the nucleophile to attack the alkyl halide because it's being preoccupied with the solvent. So again, in summary, for solvents, substitution reactions prefer polar solvents over nonpolar solvents because generally nucleophiles are more readily soluble in polar solvents versus nonpolar solvents. Now, when we're breaking down the polar solvents, we have protic solvents, which have hydrogen bonding on it, such as alcohols and water. And we have aprotic solvents, which don't have any hydrogen bonding, such as acetone, THF, DMF. Now, for SN1 reactions, the most ideal solvent would be protic polar solvents in most cases, because this helps stabilizes the carbocation through ion dipole interactions. For SN2 reactions, we prefer aprotic polar solvents such as THF, acetone, DMF, because with protic solvents, they may interfere with the nucleophile, making it harder for it to attack the alkyl halide. And again, if you take organic chemistry, you'll go a lot more in depth in why. So now if we look at this SN1 reaction, let's draw the energy diagram for it. And we'll show you the difference between protic, or two different types of solvents. Don't worry, we're almost done with this lecture today. No, it's pretty long. So we have our energy, reaction progress. So now let's do one, for example. So this is an SN1 reaction. We have our rate determining step. We form our intermediate, and then bada bing, we form our products. And let's say this one, we used, I don't know, let's pick a solvent. Let's say we used in this one, THF. So in this one, we use THF, which is a aprotic polar solvent. Again, here, we form our intermediate. Now let's, okay, we'll do the same reaction, but instead of using THF, let's use methanol, which is a protic polar solvent. Again, we start our rate determining step. And we form our products. Actually, your products would probably be the same energy. It's just hard to draw freehand with this. And let's say this one we used methanol. So you see for SN1 reactions, when we use a protic polar solvent, it's lower in energy than if we use an aprotic. And again, because that hydrogen bonding stabilizes the intermediate, which is a carbocation. Now, if we were to use a nonpolar solvent, just to show you all three, so we come here, we do a nonpolar. Oh, let's undo. So for a nonpolar, it would look something like that. It'd be higher in energy. I mean, these are just generalizations. Of course, there's always exceptions and everything. But generally, this is the trend. So this could be something like, I don't know, pentane. Again, this is for SN1 reactions. Again, down here, this should be rate equals K times that. So this is SN1 reaction. All right. Now we look at an SN2 reaction. Again, SN2, let me fix this. K equals that, equals rate. Now let's draw the energy diagram for an SN2. So this is SN2 reactions. I like red though. Let me switch back to red. Well, looks like it's blue. Let me undo. There we go. Then reaction progress. E. Again, let's start with something. Say we do one reaction in methanol. Again, it's a one-step mechanism. Cool. And we said this was methanol. Methanol, again, is a protic polar solvent. So this is methanol. MEOH is a shorthand for methanol. It's a lot easier than type of methanol. Now let's switch. And we're going to show you the same. Oh, no, undo. Just methanol. Oop. Now we're going to use something like THF, which is a aprotic polar solvent. Again, looks something. It's hard to keep my hands steady. Okay. And so with THF, you see it's a lower activation energy than methanol. Now to compare all of them, let's now use a nonpolar solvent such as hexane. Again, these are just generalizations to give you an idea of, oops, that's not good. And so here we have hexane. And there you have it. So for SN2 reactions, again, ideally it prefers aprotic polar solvents, which have the lowest activation energy compared to generally with a polar protic solvent and a non-polar solvent. So now let's look at some questions here. Here we want to know which of the following solvents would lower the activation energy of this reaction. So we want to know which one of these solvents that we use. There. Which one of the following solvents would lower activation energy for this reaction? So the first thing, we need to identify what type of reaction it is. So is it SN1 or SN2? So for that, we got to look at the energy diagram. If you notice for the energy diagram, there's only one step. So since it's only one step, mechanism, it's a SN2 reaction. So now that we know it's a one-step SN2 reaction, SN2 mechanism, we know that SN2 prefers is a good word, aprotic polar solvents. So what are aprotic polar solvents? For example, THF. THF is an aprotic polar solvent. DMSO is an aprotic polar solvent. So again, C is referred to as THF. F is called DMSO. So here we have the following energy diagram. We want to know which of the following substitution reactions would easily observe the following energy diagram. So what we need to do first, determine whether energy diagram is SN1 or SN2. So from the energy diagram, we see that there are two steps in it, and we have an intermediate. So since there are two steps, this tells you it's an SN1 reaction. So since it's SN1, SN1 prefers tertiary alkyl halide. So now we'll look to see which one is a tertiary alkyl halide. So is A a tertiary alkyl halide? A is not. A is a primary alkyl halide. Is B a tertiary alkyl halide? No, it is not. Is C a tertiary alkyl halide? No, it's a methyl alkyl halide. D, there's no halide on it. E is the tertiary alkyl halide, so E would be the answer. And the only other one that could undergo SN1, could possibly undergo SN1 would be B. But E is the correct answer. It would easily undergo an SN1 reaction because it's a tertiary alkyl halide. Next, we want to know which of the following reactions would have, substitution reactions would have the lowest activation energy using the following diagram. So again, first, determine if it is SN1 or SN2 from the diagram. So from the diagram, we see that there is only one activation energy, which means there's only one step in this mechanism. Since there's only one step in the mechanism, this means SN2 reaction. So again, SN2, we want the least substituted alkyl halides. So we got to look to see what's the least substituted alkyl halide. So A is a secondary alkyl halide. B is a primary alkyl halide. C is a primary alkyl halide. D is a tertiary alkyl halide. E is a primary, and F is a methyl. So since F is a methyl halide, it would have the lowest activation energy. Other ones may undergo SN2 reaction, but F would have the lowest activation energy for this reaction. The end. So that concludes the lecture over substitution reactions. So we have SN1 reactions, SN2 reactions. Also later this evening, I'll post a short video on elimination reactions, which we have E1 and E2, and that'll conclude chapter 16. And on Thursday, I'll be posting lectures over equilibrium.